Mr. Robert Speranzini, pardon me if the pronunciation is wrong, from Canada, and will give a very brief introduction. He is an expert in this area. Dr. Robert Speranzini is head national and international collaborations at Canadian Nuclear Laboratories, managing relationship with IAEA, OECD, NEA, that is all these international organizations which are dealing with the nuclear energy and the thorium advances, and the other countries with a focus on research and development collaboration. Dr. Speranzini serves as chair of the Research Advisory Committee of the University Network of Excellence in Nuclear Engineering and has been a member of several Government of Canada committees, including Generation 4. So I will invite Dr. Robert Speranzini for his address, please.
Good morning, and thank you very much. The pronunciation was just fine. Thank you very much.
Thank you.
And I would say I will definitely give an overview, and I would not claim to be an expert in the area of thorium research. I'm clearly more of an expert in the area of international collaboration, but it is a pleasure for me to be here today in Mumbai to present the Canadian perspective on progress in thorium R&D and to discuss some aspects of sustainability. But before I do, I wanted to congratulate the conference organizers for an excellent agenda and efforts to include such broad participation from India and internationally. Within Canada, fuel and fuel cycles have been a central focus of our research and development since the origin of CANDU's domestic program. And for those of you familiar with pressurized heavy water reactors, you know that the inherent features like neutron economy and online fueling allow for fuel cycle flexibility that includes the use of natural uranium, recycled uranium, MOX, thorium. I'll talk about fuel and fuel cycles later in the presentation, but first I'd like to talk to you a little bit about some of the recent developments in Canada. Particularly some aspects of the restructuring of Atomic Energy of Canada that led to the creation of SNC CANDU Energy and more recently Canadian Nuclear Labs. In addition, I'll summarize initially in the talk some of the other research and development work that we're doing so that you have a sense of what we're paying attention to in Canada. And really I have two key messages. One is that we've come a long way in terms of introducing thorium, particularly when we see the results of our Indian colleagues yesterday. But we have a long way to go in terms of moving towards full implementation on an industrial scale. The second message is that together we will move forward faster and likely better and cheaper. And we in Canada are certainly open to collaboration as we move forward. So as we look at the organization of Canada's industry, it is clear that our industry remains strong and vibrant, with most of the key organizations in Canada shown here. And nuclear energy is under the jurisdiction of the federal government. We have organizations like Atomic Energy of Canada and the Canadian Nuclear Safety Commission, the regulator, which report up to the Government of Canada. In addition, energy supply, energy electrical production is under the jurisdiction of the provinces. So if you see in Canada that it looks like we have a bit of disjoint policy, it is partly because we have provinces that are making individual decisions about electrical supply. Other industries that are shown here include Ontario Power Generation, which is a provincially owned electrical utility. We have Bruce Power, which is privately owned. We have SNC CANDO Energy, which now is responsible for CANDO technology, marketing, and commercial services. We also have the CANDO Owners Group, which through cooperation strives to work with utilities to achieve operational excellence. And if you look at the number of PHWRs throughout the world, there's about 47 in total at this point, and you can see that India and Canada are about tied in terms of operating units right now, and I suspect with India's new build program that you're going to quickly be surpassing the number of CANDO units or pressurized heavy water reactor units in Canada. So that's, from my point of view, very good decision and very good strategic approach. I'm going to turn my attention for a few minutes to Atomic Energy of Canada. For us, within the Organization of Atomic Energy of Canada, it's been an interesting last 4 or 5 years as the restructuring of Atomic Energy of Canada has proceeded. If you look at the origins of Atomic Energy of Canada, it is the birthplace of Canada's nuclear industry. First sustained criticality outside of the United States. We have been a Crown corporation since 1952, a strong focus on research reactor, materials research. Invented cobalt-60 for cancer treatment. We're very successful with medical isotope production. And of course, developed the original CANDO power reactor technology that supplies approximately 50% of Ontario electricity and less in other provinces. A strong, significant industry in Canada. In terms of the restructuring, it began several years ago with the first phase being the privatization of the CANDO reactor division that was previously part of Atomic Energy of Canada. So that is now a separate private organization. That was completed near the end of 2011 with the creation of CANDO Energy, which is within the SNC Lavalin fold. The most recent part of the restructuring was completed in September of this year, just about a month ago, with the creation of Canadian Nuclear Laboratories, which is operated as a government-owned, contractor-operated organization like is done in the United States. So you can view it as a national laboratory. Atomic Energy of Canada still exists, but it is a very small organization, approximately 50 people, with an oversight role. So most of the people, the facilities, the expertise that was originally with Atomic Energy of Canada is now with Canadian Nuclear Labs. And this is definitely a time of renewal for the labs. As it currently stands, we are about a 200-acre site, 17 nuclear facilities, 70 major buildings, about 3,500 employees. So it is Canada's national lab. With the restructuring, we have a firm renewed mandate with a focus that serves both government and industry. So we have a strong focus and commitment to decommissioning and waste management, the legacy liability wastes in Canada. We have a focus on S&T for government and a strong commitment to industry with major players being obviously CANDO Energy and the CANDO Owners Group. We make a distinction between S&T and R&D. In the government world, there are some aspects of policy and informing policy, but a strong component of S&T is research and development. So again, with the restructuring came a confirmation of new priorities. We have 4 priorities going forward. One with strong focus on energy, environment, health, and public safety and security. And within energy, for example, safety, fuel and fuel cycles, SMRs, for example. And while we will continue to have a very strong focus on supporting CANDU technology and advanced CANDU technology development, SMRs is there because it is a current priority of the federal government. Another example, nuclear forensics. So while we will continue to focus on fuel and fuel cycles in support of industry, those same databases can be used to support work in the area of nuclear forensics, which again is a priority of the federal government. I'm going to turn my attention for a couple of minutes to some of the major areas of focus in Canada, and one particular focus for existing CANDUs is CANDU life extension. And the major focus in that area is related to fuel channel life management. You can see that some refurbishments, reed tubes, have already been completed internationally and within Canada. So Bruce Units 1 and 2, for example, were returned to service in 2012 after life extension. Darlington is planned to start in the next year or two. Refurbishments of Bruce units are to start within the next few years. In order to extend the life of existing plants, we've paid particular attention, for example, to fuel channel life management. So we've been able, through some of the R&D work that we've done in association with COG and industry, to extend the life of existing plants. So we've been able to get regulator approval, for example, to extend operation past the original design life. So some very good success in terms of operating the CANDUs longer, and then refurbishment coming in the next while. When we turn our attention to advanced CANDU technology, we tend to take an evolutionary approach. And if you look at the split of responsibilities within Canada right now, the near-term development, the evolution of the existing CANDU technology, falls within the responsibility of CANDU Energy. The longer-term development falls within the purview of government. We have a national program which is funded by our government departments. In our Gen 4 program, we have focused on supercritical water reactor, not necessarily because we want to build one of these beasts, but because we're trying to push the limits of water-based technology. We're trying to understand what the limits are in terms of temperature, pressure, materials, fuel that we need to go to in terms of water-based technology. It also drives innovation that can be fed back into existing plants, whether it be passive safety systems or improved fuel channels. When we think about advanced CANDU technology, again, within the purview of SNC CANDU Energy, there's been work in recent years on post-Fukushima enhancements around design margins, defense in depth, containment, addition of PARs, for example, the passive autocatalytic recombiners for hydrogen management. CANDU Energy are working with CNNC in China, for example, to develop the advanced fuel CANDU reactor, which is initially designed to operate with recycled uranium, but to be thorium ready for use within approximately 15 to 20 years. In addition, there is some work on EC6 CANMUX, so plutonium dispositioning approaches. Again, within CNL, Canadian Nuclear Labs, our focus has been on Gen 4 SCWR. I won't go into details on this, but we have a concept. It is an initial concept that is a 1,200 megawatt electric SCWR reactor with thermal efficiencies pushing 50, it's direct cycle. And again, the reason that we've done this is to stimulate innovation. So we've looked at materials, we've looked at chemistry, we've looked at improved fuel channels, passive safety systems, all of which has led to innovation. One of the other aspects of our Gen 4 program has been a focus on hydrogen production. We in particular have paid attention to processes like the copper chloride chemical process, which, where we've made actually great breakthroughs in terms of tying that chemistry to SCWR temperatures. So if you go back a few years, you would need temperatures like 800 to 900 degrees centigrade in order to produce hydrogen using the copper chlorine process, but through improvements in some of the mechanistic rate limiting steps, we've been able to reduce that temperature to about 600 degrees centigrade, which is compatible with SCWR. I'm going to step through quickly some of the work that we do in the area of materials and components. And again, a strong focus on life management of components, whether it be fuel channels, steam generators, feeder pipes, some focus on cleaning and decontamination, some recent focus on smart systems, inspection, surveillance, online sensors, so that you can detect and remedy issues before it affects capacity factor. In the area of fuel channels and feeders, this illustrates some of the different aspects that we've paid attention to. So materials improvement, for example, trying to find the sweet spot in terms of deuterium ingress for pressure tubes, fuel channel inspections, different technology for inspection and monitoring of fuel channels. Feeders, we use carbon steel feeders in our primary heat transport system, and we have had issues with feeder thinning that we did not originally anticipate in some of the original designs. So we've made improvements in the materials, going to higher chrome content, for example, to minimize feeder thinning, along with optimizing chemistry, for example. Steam generators, we've had a very strong program in steam generator inspection, developing probes, but this slide just illustrates the fact that there's also attention paid to some of the software and simulation, and the point being here that with modern software you can actually have a three-dimensional representation of the damage rather than having to interpret the weird and wonderful squiggles that experts used to have to interpret. Some of the products and services, and I should say that again, coming back to our partners, some of this work may have been paid for by the federal government, some of it may have been paid for by the Can-Do Owners Group, some by industry, some by on a commercial basis. In some cases, we will develop proof of principle using federal funding and then look to our partners to help us with commercialization of our technology. So this particular unit is the passive autocatalytic recombiners. So the same technology, for example, that we have used in the past in heavy water production and detritiation are the same catalysts that can be used for managing hydrogen, for hydrogen mitigation. So these are passive in the sense that they auto-ignite and burn hydrogen before it becomes an issue in containment. Other attention has been paid to ECC strainers, for example, in response to a U.S. Nuclear Regulatory Commission concern. We provide support for retube and refurbishment, so strong focus on cutting tools, radiography, and inspection. Strong focus on reactor safety and emergency response, and I won't go through all of this in detail, but I'll mention this example, which was a Can-Do Owners Group project that was a multi-year undertaking to look at molten fuel injection into the moderator under certain accident scenarios. And this, for us, was a very unique project because we were able to negotiate with our regulator in advance closure criteria. And we had a very successful program looking at some very energetic reactions and assessing the probability of steam explosions under certain accident scenarios. So sustainability. Let me turn my attention for a few minutes to the aspect of sustainability. And we heard much of the background to this yesterday, so I won't go through it, but I think it's clear that as we move forward, future nuclear power decisions are going to be based on the complete nuclear fuel cycle. So availability of resources and security of supply, efficient use of resources, waste reduction, and environment. And some have supported a more structured approach to the assessment of energy sustainability. So this is an example of the IAEA IMPRO approach that again provides nuclear energy systems analyses. It gives you a structured approach to assessing progress towards sustainability. And in fact, we owe a vote of thanks to Dr. R.K. Sinha, because he was actually the chair of this IMPRO steering committee during the original formative years of this project, and it is clearly one of the more advanced focuses on energy sustainability. And from my point of view, one of the key aspects of this is in the first 3 bullets, and that is that it's not just about fuel and fuel cycles, because reactor technology has to advance in concert with the fuel and fuel cycles. So in the case of pressurized heavy water reactors, for example, it's not major changes that need to be made, but there are relatively small evolutions that need to be made as you're advancing your fuel cycles. So you need reactor technology evolving in concert with fuel cycles, and in addition, you need a strong focus on waste management with a discussion about whether you do a once-through cycle or closing the fuel cycles with partitioning and transmutation. And of course, we heard about those aspects yesterday. I'm not going to go into this slide in any detail other than to say that it does illustrate some of the different areas that we have been paying attention to recently. So, for example, Candu Energy has worked with CNNC in China and has a project to demonstrate the use of RU in Qinshan reactors in China, and that clearly shows the PWR heavy water reactor synergy, and several other initiatives that have been priorities for us in recent years. With respect to thorium, we have many years of experience in Canada with thorium-based fuels, paying attention everything from reactor physics to irradiation testing to post-irradiation examination and reprocessing. Our attention and the resources committed to it have ebbed and flowed over the years. In the early years, we did a lot of fabrication and irradiation testing. So our experimental experience includes irradiation in 4 reactors, manufacturing fuels with a wide variety of compositions and pellet geometries. And in all of those tests, basically the results indicate that thorium fuel has always performed either comparably to UO2 or in some cases superior performance. And again, many of the results that we have are very similar to what you saw yesterday in presentations from our colleagues from India. The behavior of thorium tends to be improved compared with the columnar kind of grain structure that you see in UO2 irradiations of similar power. which is associated with fission product release. We have flexibility with our research reactors in our ability to use this demountable bundle, which allows us to remove different elements at different times and replace them with fresh elements. So that has been a very positive tool that we've been able to use, again, tying to fission gas release, showing that the thorium-based fuels tend to have lower fission product release related to the higher thermal conductivity of thorium-based fuels. The one thing I did want to mention is that we did take a step back in 2011 with a focus of trying to regroup in terms of our focus on thoria. And essentially what we did was a gap analysis. We looked at the state of the art as we saw it. At that point, we didn't have a lot of access to information from India. We took international experience through the IAEA and NEA, went through systematically the different areas where attention needed to be paid in upcoming years, at least from our perspective. And again, I won't go through all of this, but examples of the kind of gaps that our experts have identified relate to effective microstructure, grain size, particle size distribution in terms of fabrication and irradiation characteristics of the fuel, materials properties, swelling due to fission products, grain growth kinetics. Especially lacking is some aspects of higher plutonium-based fuels. Modeling, an area of particular interest for us in the upcoming years. Fuel safety, again, a variety of areas where we should be paying attention in the upcoming years. And I think our perspective is that what is really needed is a systematic approach that looks at a variety of parameters for the whole spectrum of different thoria-based fuels, including higher concentrations of plutonium. So again, with our roadmap, really the message here is that we've done our gap analysis. We have some work in progress, but we're definitely open to collaboration and partnership going forward, whether it be through organizations like the IAEA or the NEA or bilateral cooperations. And again, when you look at the possibilities in terms of implementing thorium in pressurized heavy water reactors, there are a host of different approaches, some of which relate to mixed channels, some of which relate to mixed bundles, some of which relate to mixed pellets. We have concepts related to direct self-cycle. The point being that in the initial phases of introducing thorium, you don't actually need to recycle or close the fuel cycles. You can take time to build up the inventory of U-233 before you close the cycle. But with that, I just wanted to remind you that we have a renewed vision at Canadian Nuclear Labs. We have a strong focus on advancing pressurized heavy water reactors with, again, a strong focus on fuel and fuel cycles. And again, one of the aspects of the Thorium Roadmap project is that I think we're going to do better together than competing with each other. So again, any collaboration, we're open to the possibility with you. So with that, I'll say thank you very much and leave it. Answer questions.
Yeah.
Yeah.
So thank you, Dr. Speranzini, for giving an in-depth overview. We can open the thing for a couple of questions.
Doctor, Just wanted to know if you can correlate your Generation 4 program with some roadmap. How do you see the timelines coming up?
Well, Generation 4 reactors tend to be a bit like fusion. They tend to be always decades out. So nominally, the SCWR would be implemented in the time frame of about 2025 or 2030, but I don't really think that that's realistic. When we thought about the SCWR concept originally, one of our thoughts was that their existing fossil supercritical water industry, so existing generators, existing balance of plant, and our thought was that if we paid attention to the nuclear island, you could tie it to existing SCWR technology from the fossil industry. So one possible partner being our Chinese colleagues. I would have to say that at this point, we have, as I mentioned, we have a concept. But again, at this point, I would say that challenges related to materials and chemistry are quite significant and will likely delay any practical use of this technology in the near term. Okay.
Yeah, please.
Yeah, I have a question about the timeline for your utilization of thorium in the CANDU reactors.
Yeah, and that so again, now with the timeline, what we're doing is basically you're falling within the responsibility of CANDU Energy, and I really can't speak for them. But what I can tell you is when we look at the work that they're doing in China with advanced fuel CANDU reactors, they're looking for a new build opportunity there, nominally 8 to 10 years construction schedule, and that reactor, AFCR, is intended to be a thorium-ready reactor. So the strategy, as I understand it, is that they will start with RU, so PWR, recycled uranium, probably targeting to use thorium within approximately 20 years after the reactor starts. So you're probably looking at a timeline of about 30 years.
Yeah. So thank you, Dr. Speranzini, for a very in-depth presentation and the answers to the questions. On behalf of organizers, it is my pleasure to present you a memento.
Excuse me.